We're having a second lecture in a series given by Irene Fonseca, and she's from Carnegie Mellon University. And this is the second lecture, and it's in a series called, and the title of the series is Gamma Convergence and Applications of Phase Transitions. We are delighted that she's here to speak to us again today. And so you can go ahead and start, and thank you very much.
Okay, thank you. And thank you all for being here again. So let's continue where we left last time. And so let me remind you that what we have here is, so we have a problem on phase transitions. And what I'm dealing with here are, it's actually a mixture of two fluids. And so if it was a composite of solids, it would be more complicated. You need to have one derivative more everywhere. So this is a good place to start. And so basically you have in the background, you have a double well potential, which something which looks like this, right? And I said that, okay, I'm going to put the zeros at say 0 and 1. And so of course this potential is going to be minimized when you are at 0 at 1, and which is essentially is telling us that u equal to 0 is say one phase, say phase 1, and u equal to 1 is phase 2. So that's the first fluid and the second fluid. And you want to combine them both in a container in a way that the mixture minimizes the energy. So W is non-negative. As I said, the set where W is equal to 0 is exactly 0, 1. There's nothing mysterious about 0, 1. You can call it A and B. I've not said much about W. Later on, I may have to impose something on W. Normally, what we impose on W is that at infinity, W grows at least linearly, and that around the wells, W behaves quadratically. So you can think of it as saying that W stays C1 or C2 near the wells, right? Because the first derivative is going to be 0 since these are minima and the values are 0, so you go up to second order. But so far I have not, I didn't need any particular hypothesis on W, except it's non-negative and it's 0 exactly at these 2 points. So we had introduced an energy, which I call I epsilon of u, which is the integral over omega of 1 over epsilon W of u plus epsilon grad u square, and this is dx. Epsilon is a small parameter. And the way to think of it is that, well, okay, u equal to 0, okay, and I'm sorry, and you also fix the average of u to be some number m, which lies between the two wells. So that will force you to have a mixture. You cannot always be 0 or always be 1. You need to have a presence of both phases. Epsilon is small, and the way to think about it, as I'm just recapping what we did before, is that, okay, u is not going to be sharp 0 and 1, but it's kind of going to go from 0 to 1 in a smooth way. But of course, it wants to be most of the time at 0 or at 1, right? So you want it to be like a 0, like a 1. So this will be u equal to 0, this will be u equal to 1. And in between, you're going to have a transition, a smooth transition, say on a layer with epsilon. And this is a back of the envelope calculation that we made last time to justify why these scalings, why do I put the 1 over epsilon here and an epsilon there? And you may recall that that for this particular setup or this particular shape of u, I would get that this energy here would be actually of order 1, which is good because we don't want anything that vanishes on us. We want, eventually we are going to look at the limit of these energies, at the asymptotic limit of these energies. Okay, so And so the question that we ask here is, so if I let epsilon go to 0, so if I let epsilon go to 0, where do these energies go? What is that limiting energy? And does that provide me a selection criterion? Because remember that we also said that if I just leave it like this, any function u, so if I just take, say, I of u to be the integral of w of u, of course, that's minimized whenever this is actually 0, if u is the characteristic function of a given set E. So that's, as you know, that's just 1 if x is in E and it's 0 otherwise, provided that E has the right measure, which should be m times measure of omega. Omega here is the container, and it's an open bounded domain, nice domain. Okay, and we also said, well, if I just leave it like that, I have infinitely many solutions. There's too much non-uniqueness, and what we hope is that basically we're penalizing here. What this term is doing is penalizing interfacial energy, right? Because it's only non-zero at when you move, or when you're changing from 0 to 1. The gradient is identically 0 here. There's no contribution here. There's no contribution there. The only contribution of your gradient is exactly here, okay? And that's where the interface is going to be between 0 and 1. Okay, so we have a program for this. Okay, so then the goal is to identify what is this limit here, and if indeed does that give us a selection criteria. There is that this process will identify among all possible such use a particular one. Okay, so the program, which I kind of announced before, goes like this. If you wish to roadmap, goes like this. First, we need to prove that for every epsilon positive, I epsilon admits a minimizer. May not be unique, okay? But say it is a minimizer, and I'm going to call it U epsilon, okay? Then I want to show that up to subsequence, which I will not relabel, U epsilon converges in some topology to some U, and U has the good taste of being one of these functions. So U of X, oops, belongs to 0, 1, almost everywhere. Okay, by the way, if in particular, sorry, I have to. If in particular, and I want this convergence to be such that in particular, I have pointwise convergence almost everywhere. And you may recall that this is something we did last time, that we already proved that if you have this, we already saw that if indeed the U epsilons converge to U pointwise almost everywhere, and if they are uniformly bounded in energy, we already proved last time that was using Fato's lemma that, so this was using Fato's lemma, and here all I used was that W is continuous, and I'm still going to assume that W is continuous, at least. at this point. Okay, and we proved that then you would have this fact for free, that these would come immediately. Okay, so that's good news. In point 2, half of the work is already done. Then the third, okay, so this was actually what I'd like to call 3. So 3 is done. And then 4, we need to characterize what is this U. So what makes this U special? Okay. And actually the way we do that is to show that, so how we do this, we show that the energies I epsilon gamma converge to some energy I, and gamma convergence is on the title of this series of lectures. So gamma converges with respect to some topology, which we'll come back to that later. So we want to show this, and then we want to show, we want to characterize I, we want to have like a representation for I. As explicit as possible for I, and then we want to show that that function U minimizes I. Now, the good news here is that this part here is for free. And it's for free because we will see that whenever, this is a fact, it's a fact from the theory of gamma convergence, that if I epsilon gamma converges to I, if U epsilon minimizes I, and if U epsilon converges to U, and all this should be with respect to the same topology. So let me call it tau. With respect to tau. If you have the convergence with respect to tau, then U minimizes I. This has nothing to do with the problem that we are dealing here. This is a generic fact of the theorem of gamma convergence, which goes back to the Georgi, Anu the Georgi. So, but we'll see that. It's a simple fact. You're going to see that it's a simple calculation, but that's a generic fact. So the last bullet is done. What we need, but we have still 2 bullets on point 4 to deal with. Okay. So very good. So let me start by going to point 3. I'm not going to do this in order, but of course this is the roadmap, right? But I'm not going to do it in order. I'm going to go to point 3, and I'm going to convince you. Okay, so by the way, this is called compactness in general. That's in the theory of gamma convergence, if you wish. This is called compactness. That is that compactness is exactly what it's written here, namely that sequences which are energy bounded up to subsequence, they converge. Okay, that's so-called compactness. So, but we need two ingredients here, right? So first, I'm going to first show this one. I'm going to assume that I have a minimizer, which I didn't prove yet. I will prove, right? I'm assuming 1, and I'm going to prove that indeed they are uniformly bounded. So let's start by doing that. Okay, so assume 1, i.e. U epsilon is a minimizer of I epsilon. And my claim is that, okay, so then indeed, the if, actually, excuse me, the soup, because I want the soup in epsilon of I epsilon of U epsilon is some number which I'm going to call M, which is finite. And you may recall that was a crucial point for us to deduce that if that was the case, then you would have to be just 0 or 1. We use that fact. Okay, so let me, and I'm going to prove this. Instead of proving it in general, I'm going to use a prototype W, a very simple domain. I'm going to do that on the line, but this can be done in Rn with generic Ws for which I only have some growth conditions and things like that, okay? So, so I'll do this in a particular setting, but it will be easy to see why this works. So I'm going to take omega to be, say, 0, 2. I'm going to take W of t. Actually, this was a prototype which I mentioned last time. I'm going to take it to be t squared 1 minus t squared. So yes, it has U's at 0 and 1. It's non-negative. And the mass constraint is, I'm going to assume that I only deal with fields which have average equal to 1/2. Okay, so in between the ones. And I'm going to come up with a competitor, if you wish, which is going to look like this. It's going to be, so I'm going to put a 1 here, a 1 minus epsilon. I'm going to be a 1 plus epsilon. And then I'm going to have a 2 here. And it's going to look like 0 up to 1 minus epsilon. Is going to look like 1 between 1 plus epsilon and 2. And it's going to be linear in between. Okay, so let me put some other color, let me put purple. So it's going to be linear here. Actually, I'd rather put here the red, because these are the ones. Okay, I'm going to call this function V epsilon. Okay, so V epsilon, I can write it explicitly. So V epsilon of x is exactly 0 if x is between 0 and 1 minus epsilon. Is going to be epsilon minus 1 over 2 epsilon. This is simple calculation. If x is between 1 minus epsilon and 1 plus epsilon, and then it's going to be 1 if x is between 1 plus epsilon and 2. And this is the typical way you do that. You just take a function which is admissible. You prove that these functions have finite uniform energy. So a minimizer would also have to have, because if anything, a minimizer would minimize, would have lower energy, right? So first, that V epsilon is admissible. And indeed, if you calculate, let's see, so if you calculate the average over omega of V epsilon, well, the measure of omega is 2, so it's 1 over 2, 0 to 2. And then what do we have? V epsilon, right? And then I can break these. I'm just going to go this slowly. So it's 1 minus epsilon to 1 plus epsilon. And here you get, oops, I keep doing this, epsilon minus 1 over 2 epsilon plus 1 over 2 epsilon x dx. And then you also see this part here, right? Which is just 1, it's just 1 minus epsilon, which is the length times 1, right? And then you integrate these, it's a simple exercise, and what you get is exactly a half. Okay, which was my M, right? So this was my M. So it's admissible. Okay, that's a simple calculus 1 integration. Okay, then you're going to calculate the energies of these fields and what you get. So you have the integral between 0 and 2 of 1 over epsilon, W of the epsilon, plus epsilon well, in this case, it's the derivative v epsilon prime square, right? And the only thing you see is what happens here, because w is 0 here, w is 0 there. The derivative is 0 here, the derivative is 0 there. So everything is happening here, right? And so you get 1 minus epsilon to 1 plus epsilon. I did this computation, so it was 1 over epsilon. And it was t squared 1 minus t squared. So t squared is epsilon minus 1 over 2 epsilon. It was 1 over 2 epsilon x squared. And then 1 minus epsilon minus 1 over 2 epsilon minus 1 over 2 epsilon x squared. And then it was a derivative. So that is the first term. And then I'm going to add 1 minus epsilon to 1 plus epsilon. And then I have the epsilon here, which is this epsilon. And then the derivative, which is just 1 over 2 epsilon squared. Okay. And well, a simple observation is that actually this is below 1 in that interval. This is below 1 in that interval. So I can go up with the amplitude of this interval here, which is, so I get the 1 over epsilon from here, 2 epsilon from there. And then you get this derivative, this integration here, which is exactly when you integrate, you get something like 1/2 if I'm not wrong. So totally it will be 5/2. It doesn't matter what it is, it's finite. But the bottom line is that since the epsilons are minimizers, you get that I epsilon of u epsilon is below this particular one because a competitor. And so bottom line, the supine epsilon of the I epsilons, which is what I call M, is at most 5/2, which doesn't matter what it is, but it's finite. Okay, and that proves what I wanted. Right, so that proves this part. That proves that proves this part here of the compacts. Okay, so you already know 3. We know 3, so 3 is done, right? 3 is done. We already proved these also, assuming that I have a minimizer, which I have to prove. Okay, now let's look at 4. 4 is, what is this I? What is this gamma limit? And okay, so let's look at 4. So we are going to find, we will see that this limit is asymptotic limit, energy I, is actually going to be, which is something I announced already before, it's going to be a constant times the perimeter or the phase where u equal to 0 in omega. If u takes only value 0 and 1, and of course, if the average of u is m, it's plus infinity elsewhere. We will see that, by the way, the perimeter where u is equal to 0 in omega is exactly the same as the perimeter where u is equal to 1 in omega. And again, simple cartoon here is that if you take, say if these are patches, I don't know if this was the same picture I had before, but it doesn't matter. But if I put u equal to, say, 0 here, u equal to 0 here, u equal to 0 there, and maybe there, and then I'm going to put u equal to 1 elsewhere, right? Then so u equal to 1 will be here. Then I'm going to count the perimeter where u equal to 0 inside omega does not see the boundary of the container. So it's going to be, I don't know which color I should use, but let me use purple, for example. So it's going to look, or actually this looks like a red. So it's going to look like this, like that. So it's basically the length, the surface area. But you see, you don't count this part of the container, which would be part of the perimeter. Okay. The perimeter is the same as basically surface area. Okay. So this is also another way of writing this is writing this with the Hausdorff measure, dimensional measure of, excuse me, this is the perimeter. Okay. That would be like of the boundary where u equal to 0 intersection with omega, right? That's the Hausdorff measure. N-1 dimensional Hausdorff measure, which, as we mentioned before, if you are on the line, the H0 measure is just the counting measure, you just count the endpoints. If you are on the plane, it's just length. If you are in R3, it's surface, and so on. Okay, and in addition to that, so sigma here is what we call, so that's the actually isotropic. It does not depend on the normal. Is isotropic surface energy density. And actually, we can calculate it explicitly. It's going to be twice the integral between 0 and 1 of the square root of W of SDS. But we'll see this. Right now, just trust me. Okay. Now, and again, this was also something we mentioned, which was that this procedure, this gamma convergence procedure, selects those U's for which these phases are nice, and you can actually compute the perimeter, because they could be really bad. They could be like fractals. They could be very noisy, but no, they will have very nice properties. You can even talk about normals to these surfaces and so forth. That's the so-called set of finite perimeter. So if you wish, I will say that U is equal to the characteristic function of a set E. Again, E, the measure of E has to be M times the measure of omega, and E will be a set of finite perimeter, which is another way of saying that the characteristic function of E is a BV function. It's a function of bounded variation. I apologize for the noise, but they are basically destroying a tree in front of my house, and there's a whole thing going on here of bounded variation. Okay, but we'll come back to that. So, okay, I keep talking about gamma convergence. I didn't tell you what it is, right? So that is part of 4, right? Because in 4, we have to show that there's a convergence in the sense of gamma convergence. So I have to first tell you what do I mean by gamma convergence. So let's have a very short crash course on gamma convergence. Oops. Okay. So, so you have some family of functionals I epsilon. I'm designating with the same way that we've been dealing with, but this is abstract. They don't have to be written in terms of integrals. It doesn't matter. It's a family of functionals from a certain function space, say, into the reals. Actually, let me put not just reals, because, for example, we are saying that they are plus infinity if the constraints don't work, right? So let's extend to plus infinity to allow for constraints. So say, is this not writing? So minus infinity. But I can include plus infinity because, as I said, if the function does not satisfy the constraint, in this case, the mass, I take I epsilon to be plus infinity. And X is a topological space. Right. So when do I say that and now let me take another I. By the way, and here, word of caution, our I epsilons need the function need to be very nice, right? It's a Sobolev function, right? I'm talking about gradient and all that, and still the limit function is going to be a characteristic function, right? Okay, so that's a note. I'm going to take, so X has to be the broad space where I land. So it's going to be the space of, which would be BV. Actually, it's going to be characteristic functions, but it's a special case of BV, which means that when I define I epsilon, I'm defining I epsilon to be 1 over epsilon W of U plus epsilon grad U square dx. If first I want U to be Sobolev, in this case H1, or if you wish, it's the same thing as W12, and average equal to M, and it's plus infinity otherwise, right? So the effective domain of I epsilon is smaller than where I land, and normally that happens with gamma convergence. You need a larger space when you land. Okay, so you have I epsilon and you have I, and now when do we say that I epsilon gamma convergence with respect to tau, and we write it like this, to I, and when tau is obvious, you don't write tau, if the following hold. First, that's a so-called gamma limitive property. If I have a sequence V epsilon converging in the sense of tau to V, and this convergence could be a weak convergence, okay? I'm writing with the full arrow, but it could be half arrow if you only have full convergence, right? It's whatever is with respect to topology tau. Then you want that I of V is below the limitive as epsilon goes to 0 of I epsilon of V epsilon. And 2y is the gamma limit sup property. And so. Which tells you that if I take a V, a target V, right? So in our case, possibly discontinuous, then I can find a sequence W epsilon. So you can think of this one as being discontinuous. You can think of this one as being much smoother, actually Sobolev. But of course, it depends on the setting. But I'm just going back to what we're talking about here, such that I of V is actually bigger than or equal to the limit sup of I epsilon of W epsilon. And then you pause and say, hey, wait a second. So what am I saying here? I'm saying that, I of v is bigger than or equal to the limit sup of I epsilon of W epsilon. Well, that's property to I. Well, but the limit sup is always bigger than the limitive, so that's bigger than the limitive of I epsilon of W epsilon. Oh, but now I can use property I, right? So by property I, that's always bigger than or equal to I of v. And if you look at this string of inequalities, well, you better have equalities everywhere, right? So that means that, you know, the upshot is that indeed I of v is actually a limit of I epsilon of the sequence W epsilon. And you call these, you call such sequences recovery sequences. This is a recovery sequence for V. And it does not have to be unique. In general, it's not unique. Okay, so now I told you that every time that's a fundamental property of gamma convergence, let me see if I keep track of the, I still have 10 minutes, right?
Yes, maybe about 12 minutes, yes.
So this is something I already announced, and I'm going to prove to you. And remember that I said, oh, you know, there's something that you always have for free, namely, if I epsilon gamma converges with respect to tau to some I, and if U epsilon minimizes I epsilon, and if U epsilon converges with respect to tau to some U, so if you have these three, then you will minimize I. So limits of minimizers are minimizers of the limit. And this is something that I already mentioned to you before. And now I'm going to, with a simple back of the envelope calculation, tell you why. So
sorry,
why?
before you can I have questions on the definition?
Yep.
The sequence omega epsilon, do you have that one converge to V or no?
Oh, yeah, I'm sorry. Of course, yes. With respect to tau.
Okay, thank you.
Okay, just as there, okay, of course, no, thank you. Yeah. So it's a converging sequence, but at the end of the day, actually does realize it linear. So as I said, limits of minimizers are minimizers of the limit. Let me tell you why. Okay. Now, U epsilon converges to U. So by I is the gamma limit inf, right? So I of U needs to be below, right? I'm going to call this star because I'm going to come back to this. My claim is that for all V admissible, I of U is below I of V, right? I'm trying to prove that it's a minimizer. So that's what it is. That's my claim. Okay, so pick a V, an arbitrary V. So fix V arbitrary in X. And now I'm going to use 2i. Remember 2i is that I can always find a recovery sequence, right? It's even better than limit gamma than the limit sup. It's exactly the limit, right? It's 2i. It was the upshot here. So by 2i, I know that I can find a W epsilon, which is a recovery sequence for V, in that W epsilon converges in tau to V, and I of V is actually the limit of I epsilon of W epsilon. Okay? So, okay, so then now it's a string of inequalities. So I of V, I just wrote, it's the limit in epsilon of I epsilon of W epsilon. Oh, but remember, the U epsilons minimize the energy, right? They minimize. So then I can go below with the limit, actually sup if I wish, of I epsilon of U epsilon. That's because the U epsilons minimize the energy. Right? Well, okay, but a limit sup is always bigger than a limit if. And this one, we already saw in star, that's bigger than or equal to I of U. Done. Okay? So I proved that indeed I of U is always below any I of V. So you see that's automatically we get that from the definition. Actually, I claim, so that let's put it claim 1. And claim 2 is that I can do better than star. In the sense that if I have a minimizing sequence converging to a U, then actually star is going to be an equality. You cannot have a gap. And let me show you why. Okay. Now, again, let's think about what I call 2i, right? 2i was the recovery sequence. I take Q, and I'm going to call, say, Z epsilon, a recovery sequence for U epsilon. Then what I have is that I of U is going to be equal to, that's 2i, the limit in epsilon of I epsilon of Z epsilon. But again, the U epsilons minimize the energy. Right? And again, that's bigger than or equal to the limit of I epsilon of U epsilon, which again by star or by I, whatever you want to call it, that's I of U. So again, you have to have equality here. Right? You need to have a string of equalities. So what I'm saying here is that the minimizers will always be a recovery sequence, will always constitute a recovery sequence for the limit, but that does not mean that every recovery sequence for you is a minimizing sequence, okay? So,
Did you mean to have recovery sequence of U epsilon or recovery sequence of U?
Of U.
Yeah.
I'm sorry, okay.
Yeah,
So
yeah.
So we mark.
I'm just saying, when you say you're trying to do better, you have a recovery sequence.
Well, I tend to do better because a priori, with this information that I had here, that U epsilon converges to U, a priori I can only say that I have this inequality, right? That was property I.
But
I think
what I was confused about the notation a little bit below when you had,
Tell me
when
where.
you choose the recovery sequence, maybe it's the recovery sequence for U, not the recovery sequence for U epsilon. See, slide down a little bit. Yeah, right there.
yeah, right there.
Let's see epsilon recovery sequence for U. Yeah, there we go. Yeah, okay, that's good.
Oh, sorry, no, of course. For you,
Okay.
right?
Yeah.
It's
I have a small question.
that's here. Yeah.
A conversion with respecting to tau is exactly the thing with conversion with respecting to the total variation.
I'm sorry?
So so you have the conversion with respecting to the topology tau, right? Is that
Yeah.
the same with the conversion with respecting to the total variation?
Well,
Variation.
it depends on the problem that you're dealing with, okay? In our case, it's going to be actually with respect to the L1 strong topology,
Okay.
but it depends on your problem. It does not even have to be a metrizable topology. What I've been saying until now works for any topology, okay? It's an abstract concept. In our case, we are going to use L1 strong topology. We're going to say that U epsilon goes to U if the integral of mod U epsilon minus U goes to 0. And I'll justify why, okay? And from problem to problem, the topology will vary, will not be the same, usually, okay? The topology depends on the problem that you're dealing with, okay? So minimizing, so okay, so what I'm saying is that minimizing sequences are recovery sequences for the limit, but there may be recovery sequences for the limit, which I called U, which are not minimizing sequences, okay? For example, if you add a little order of epsilon, right, you still converge to the right thing, but still it's no longer minimizer at the epsilon level, right? Okay. Now, so now, okay, now I think I'm at my limit, okay, because what I want to do next is point 1. Point 1 was that, remember, is this. Point 1 is that each I epsilon admits a minimizer. So I still, so I introduced the concept behind this, but I didn't tell you yet what is our gamma limit, but I did the groundwork for this. Of course, this is completely open yet. This is done. This part is done. This part is done. And now I'd like to look at this and prove that for every epsilon, I epsilon admits a minimizer. So probably I just announce and that will be it because I won't have time to go over this. But let me just announce what we're going to do next. So next, we will go over 1. So prove 1. And we are going to do that using the direct method. Oops. Of the Coxo variations. So first, I have to give you an abstract tour of what is this direct method. which again, I'm going to set it up in a very abstract setting, general setting that has nothing to do with our problem. And then we're going to apply to our problem to prove that indeed for every epsilon fixed, there is a minimizer, which is what we've been calling U epsilon, okay? But first I need to introduce this concept here of the direct method of the Cox variations, which is very powerful. And there's very little that you do in the Cox variations without using the direct method, okay? But I think I'm going to leave that for next time because it will take more than a minute or two. Okay, so I'm going to stop here. And I don't know if there are more questions.
Yeah, I had a question just about notation.
Yeah.